Our next talk will be by TQ, Calvin, and Tech Fury, which would have been far more difficult actually if we would have met in Leipzig, because TQ is originally from the US, now he lives in Belgium. Calvin is from Canada, and Tech Fury is from the US. So this would have been far more difficult to do in person. TQ it has been into retro computing for around 20 years, starting with the TRS-80, moving over to mini computers, and yeah, he's especially interested in the features that died with that market segment. Calvin from Canada started retro computing also as a hobby, and he lives the dream of most of us because he got to make a job out of it. So he works with the more modern iterations of the systems he started out with as a hobby. And Tech Fury is a daytime shipment tracking software developer and a nighttime necromancer for weird old hardware. And together the three will talk to us about what have we lost, features of mainframes, and so on.
Good evening, everyone. Let's talk about some fun old shit you can learn from at home. Your hosts tonight are Calvin Buckley.
Hi. On my day job, I just basically do a whole bunch of PHP hacking on IBM. Spoiler alert, we're going to be talking about that. And at night, I basically enjoy preserving software for future generations. Apparently, there's also this guy called TQ.
Hi. By day, I build a distributed trust system for computers, and at night, I figure out how to make old computers feel comfortable in a modern world. And there's also Landon.
In my day job, I maintain an in-house iOS app. And at night, I'm a curator and aficionado of bygone Japanese and British computer systems, like NEC, PC-98s, Acorn, Archimedes, etc. And with that being said, let's hand off to TQ with his presentation on the Symbolics Lisp machine.
So, in the early 80s, MIT spun off part of its research group into a firm that produced Lisp machines. That firm was called Symbolics. They built a machine called the Symbolics 3600 that ran an operating system called Genera. What exactly was this? Well, obviously, based on the name, it's a Lisp machine. It's got hardware that runs Lisp directly. Everything that ran on the machine was written in Lisp, from the microcode to the operating system, all of the drivers, everything. It included all of your development tools that you'd expect. The editors, or your editor, your compiler, your debuggers, inspectors to be able to look at data structures, all in Lisp. And it was, for a very long time, considered to be one of the best development environments around. It ended up dying a sort of ignoble death because, for a combination of reasons. First of all, the company made some absolutely terrible decisions. They ported their platform to run on NuBus on Macintosh shortly before Apple switched to PowerPC and PCI. And then they went from there to the architecture of the future, Alpha. And then they died. We're not here to talk about the death of Symbolics. We're here to talk about their life. Let's talk about their first machine, the 3600. Shipped in 1983. It had a 36-bit word, 4 bits of which were set aside for tag bits to tell what type of data was stored in a particular word. And the other 32 bits were for the value of that particular word. The processor microcode had 36, or the processor microcode had up to 16 hardware tasks to be able to handle things like interfacing with the disks, driving the display, scanning the keyboard, accessing the network, etc. That microcode also provided a high-level instruction set that had instructions like const to allocate memory and garbage collect if necessary. It also had your usual complement of arithmetic instructions, add, subtract, etc. But unlike most architectures, even modern architectures, the arithmetic instructions operated on arbitrary precision words, even possibly rational numbers. At one point, they ported a C compiler to it. It just used the native machine integers, because why not? And somebody tried to run a program that determined the size of the word by shifting one left until it ran off the end. And this program ran for about an hour until it ran out of memory. So, I could explain the interface, but it's probably easiest to start with a demo.
When you start up Genera, you're greeted by a pretty high-resolution graphics display. The original machines shipped with an 1100 by 900 resolution screen, so this full HD display that you're seeing right now is not far off from original hardware. With so many pixels to play with, it may actually be surprising that the entire display is taken up by a command line. But this is not the Unix command line that you're used to. We'll start by logging in. That's what it tells us to do. And immediately we see that there's a significant difference. Normally with a Unix command line, you type in a command, cp, ls, whatever, and it just waits for you to type in the rest of the command. If you need to give parameters, you need to already know what those parameters are, possibly looking them up in a man page. Genera, on the other hand, Genera holds your hand a bit more and prompts you. You need to enter a username. Okay, I'll do that. Okay, so what can we do here? As any Unix user knows, the first thing that you do in any terminal, whether you've just changed the directory or whatever, first thing you do is do ls. Genera spells it a bit differently, and I'm going to list my home directory, which hopefully is already selected. This still looks very much like a traditional Unix directory listing. But you'll notice that as I mouse over it, it actually highlights individual lines. And this is the first hint that there's something really special going on. Suppose that I want to list the contents of one of these directories. I'll type in show directory. You'll notice, actually, that I just typed in the first couple characters and it auto-completed. I want to list the Lisp directory. And I could type it, but it's already on screen. I should be able to just click it. And when I do, it pastes it into the prompt, and I can hit enter to accept it. That just lists the directory itself, which is not quite ideal. Wonder what else we can do. What happens if you just click it directly? That actually lists the contents. And you'll notice that it actually filled in a command for me. It says show directory Genera VLM home the Quux Lisp /*. What has actually happened here is very subtle. Each of these objects that is shown on screen has a set of handlers attached to them, and when I click on them, the system knows a command that should get run. Such a command could be bound to the left mouse button, which is what you'd expect. It might be bound to the right mouse button. In fact, at the bottom of the screen here, you can see, well, I can't actually point it out, but you can see that if I press the left mouse button, it will execute show file. If I execute the right mouse button, it will show a menu. And there's a bunch of other commands. So now that I've shown the contents of the Lisp directory, let's say that I want to actually show what is in a file. Just type in show file. And we'll get to these files later. For now, let's just look at this file 1 and file 2. Paste file 1, and it shows the contents. It says, no need to get catty, which makes sense. This is basically the equivalent of cat. I could have done the same thing by just clicking that without typing in the command first. I have other options too. I can open up an editor. I'm going to resize the current window. And open an editor and move that aside so that I can see the window underneath. This is Emacs. As you can probably guess from the name, it's just an Emacs clone. The Z actually stands for Zwei, which in turn stands for Zwei was INA initially. And in case you're curious what INA stood for, INA is not Emacs. It's all in good pun. Being an Emacs clone, we can open a file with Control-X, Control-F. We know that we want to look at file 1. So we can click it, and it opens. Earlier, we clicked file 1, and it printed it down below. If the active window is a Emacs window, though, we can click another file, and instead of printing it in the Lisp listener, it opens it. This shows that each window has an input context associated with it, and the input context controls what commands will be automatically executed when you select or interact with some object that's on the screen. I'd like to point out one more feature of the command line. I remember reading that Lisp was widely seen as the language to implement advanced AIs in, and I decided that I didn't care to actually write this talk. I wanted the system to do it for me. It's Lisp, it's good at that. So I made a command. And it asks me what I want to give a talk on. I'm giving a talk on Genera for now. I click that, and it asks me a couple more questions. Do I want to talk about presentations? Yes. Do I want to talk about the inspector? I might have time. Let's see. Ooh, what do I want to inspect? I can click hit this and type in a function, the results of which will show me later. I'll skip that for now, because chances are we'll have enough to talk about that I won't actually have time to get into that. Do I want to talk about documentation? Yes. Cool. Let's do that. And as it turns out, I didn't actually have time to make an AI to write the talk for me, so, oh well. So let's take a look at what the code that created that looks like. Here's the source code. All I did is I declared a couple of variables. I called the accepting values function, and then asked a series of questions. Whether some of the questions got asked depends on the answers to some of the earlier questions. You may recognize this pattern. This is exactly the same way that you'd write code for React or Dear IM GUI or any of the many modern immediate mode GUI frameworks.
What have we learned? Interesting things that you saw there that you should really keep in mind. The things that you should remember from that demo are that Genera had a pervasive command line interface that integrated very, very well with the graphical interface, and that everything that got displayed on screen represented an actual object, and you could manipulate those objects based on the things that appeared on the screen. Let's look at an alternative implementation of the same idea, just from the West Coast. Lando?
And on the West Coast, Xerox actually invented its own sort of Lisp machine. They originally ported BBN's Lisp for the PDP-10 as people moved over to Park from the East Coast, who used to work at BBN MIT. Then they ported it to the Alto at Park using a bytecode virtual machine implemented in the Alto microcode. Then it got ported to the successors, the D machines, which they called because they had names starting with the letter D, Dandelion, Dorado, Daybreak, so on and so forth. And since the Interlisp D team was near the Smalltalk team, many of Smalltalk's concepts, like overlapping windows, made their way into Interlisp D. And as happened with Symbolics, Interlisp D was also the victim of the AI winter, and it never really thrived after Xerox sold it off in '88, but recently Xerox has open sourced it. Now, since the D machines were actually originally meant to run Xerox's Mesa virtual machine, and they kind of just hacked Interlisp onto them, they're more or less just a simple 16-bit microcode stack machine. Not really that different from a lot of 70s mini computers, just kind of in a workstation form factor. So they aren't as fast. There's a lot less fancy features. None of these fancy tagged pointers, none of that. But it worked, and it was a lot cheaper than Symbolics. Eventually, a team at Fuji Xerox actually implements this virtual machine in C on top of Sun OS. And it's actually now open source, and you can run it on your common x86, ARM, whatnot systems today. Just get it off GitHub. So just like East Coast Lisp machines, Interlisp D is also a complete operating system, again, written entirely in Lisp. However, there's no Emacs for the editor. It's a little bit different on Interlisp. Interlisp's code editor works by editing S expressions directly in memory. It's not a text editor. It does not touch source files on disk at all. You just merely edit your S expressions directly in memory and then just hit done, and it automatically commits the changes in memory, but it requires a further step to save them. And also, Interlisp D provides TEdit, which is a rich text editor that was inspired by the famous Bravo editor on the Alto. And now, let's see Interlisp D for ourselves. Let's start up Interlisp D. You can try this at home. Everything I'm about to show you can be done with just the materials on GitHub. As you can see, this is a bit more like Smalltalk than Genera in terms of aesthetics. We have draggable and resizable windows, just like modern windowing systems. We also have right-click context menus. They've been around a while. Now, note that this environment looks more or less the same as Interlisp D did in the 80s. They haven't changed a whole lot. So anyway, in the exec menu, we can pull up a REPL. We have Xerox Common Lisp, a strict Common Lisp mode, and we have Interlisp. So let's pull up an Interlisp REPL. All right, so let's customize our environment a little bit. This background's kind of plain. So we're going to use files load, *bg to load in a program called *bg. But we don't know what the name of the function we need to call is. But we do know that there's a variable called the *bg comms, and that's kind of like a package manifest where all the variables and functions are grouped together. So what we can do is we can pull up the editor on *bg comms. Now this is SEdit. SEdit's a little interesting, as I mentioned earlier. This is not a text editor. This editor is actually editing the S expressions directly in memory and formatting them as code. So the nice thing about this is that we change the size of it. As you can see, the code automatically is formatted to fit the different sizes. Now, let's look at our functions down here. See, it's in the function section. Again, notice as I double click on things, the scope expands. I thought that was pretty cool. So let's see, *bg, this looks similar. So we'll select that, see how it's underlined, and then we will middle click on the menu bar here. We can choose Edit, Functions, and take a look at that. That's the function *bg's code. Now let's run it. And you see we have this nice little space-themed background. Now let's do a little bit of editing. This is a little bit of a famous demo here, sort of. You see this a lot in old brochures, and why is the mouse being very laggy today? It's kind of strange. Famous has the Interlisp D logo, but I think we should change some things about. So why don't we, since we know we called Koto logo W the function, we'll do df define function, which also edits Koto logo W. Now we could just simply use some of the arguments, such as a string, but let's just hack it. So we're going to change the Interlisp D. Hi, rC3. And then we're going to go to the SEdit menu. We're going to choose Done. This commits the changes, but only in memory. So it has not changed the file that's loaded from. Let's run the logo again. Hey, look at that. Hi, rC3. Now, so like I said, it doesn't save them to disk. So if we do files ? It notices that we've made changes to the Koto logo W function in the Koto logo file. And if we do make files, we've now saved it. And we can also try this. Let's see how this works with the new function. Let's try df hello. I'm going to do a little bit of a hello world function. Do this old school entry list style. So we're going to use lambda. See, template's already filled out. We're going to highlight this argument. And then we're just going to hit forward delete. And then see how that's cleared out. And we'll do the same here. Notice when I type the closing parent, it just simply closes it. It doesn't insert anything. I can't just type more. And this is very structured, this editor. You do done. Now we have our hello world function. And if we do files ? Again, it's going to ask where we would like to put it. Oh, it's beeping at me because it's a yes or no question. They do a lot of things like this in Entralip. So we'll just hit Y. And we'll give it a name, hello2, create a new file. And you can see the changes are marked in there. It's already created a hello2 comms. Let's take a look at that. So you can see it's already built a package with just the function hello, which is the same hello as we see there, as we will see when I pull up edit. Same thing. So, moving on further from that, we can also do, to save it, make files. And we can also explicitly do that with makefile. Again, and notice there's a version number. This is inherited from TOPS 20, which is what they ran this on originally before they ported it to the D machines. Now let's take a look at the tedit document editor and the file browser. So if we right click on here, we can choose the file browser. And we're going to give it medley. Notice the use of the greater than symbol for the path separator. So all right, we're going to take a look here. Table of contents. This is the Lisp users library. This is basically contributed programs from users. So we select it like such there with the left button. We're going to go to Edit, Tedit. Ask us to define our window. See, take a look at this. This is Tedit, rich text editor, kind of getting a little bit of a generic document examiner vibe here almost. And it's, in fact, a complete rich text editor. Let me see if I can get the, here we go, expanded menu. Page layout stuff. You can also quit it. Close that window. And similarly, most of these entries, like say star BG we were looking at just a little bit ago, let's find that. Similarly, it has its documentation available through here. Now, similarly, we also have a language reference manual available through dinfo, and that too also appears to be based upon tedit. Let's go ahead and actually close tedit there. All right. So you can navigate through this. It's all hypertext style. And then, we almost forgot about dwim. Dwim is pretty cool. Dwim is do what I mean. And so remember how we typed hello, and that has to be in all caps because Lisp is case sensitive in this regard. But let's see what happens if I type it all lowercase. It suggests for me automatically that perhaps I meant all uppercase, or I could tell it it's wrong, undefined function. And similarly, as you might expect from a virtual machine, virtual memory persistent setup, you can also simply log out, which just got dwimmed again to all caps, and then that will save the entire world. and we can pull it back up again just exactly where we were. And that's it for the Interlisp D demo. And now we will go on to our next and last platform I will be demonstrating today, Btron, Japan's attempt at designing their own desktop operating system from scratch. But what is Btron? It's an outgrowth of the Tron project, which basically was a Japanese academia industry initiative to develop a new set of operating systems and standards for a computerized society of the 21st century. And they came up with all sorts of standards like the Tron keyboard. They even have CPU architecture. The end goal of all this was to have essentially a world in which all of the objects in your everyday life would be based on Itron embedded operating systems, interlinked through a network of Ctron machines to your Btron-based desktop computer. And so Btron is known as BusinessTron. It has a desktop metaphor. It's meant for personal computers, has a heavy emphasis on working with documents. And one implementation of it is still sold today as a VMware image. And speaking of these futuristic systems that sound awfully like the Internet of Things, I highly recommend watching this Tron Smart House video I've linked here. We couldn't fit it in here. There wasn't enough time, but you will see that the Internet of Things is really nothing new as a concept, and that these guys even thought as far as the Internet of Things toilet back in the day. So one of the unique features of Btron is the Tron application data bus, which defines real objects and virtual objects. Real objects are a type of structured container file. They can contain any number of embedded virtual objects or links to other virtual objects within other real objects. Btron additionally calls for a unified document editor in which various basic objects can be freely mixed and embedded. For instance, you can actually use an embedded spreadsheet object as a table, and system updates actually are shipped as documents. And speaking of system updates shipped as documents, we're going to actually show you how to install one right now in this demo, right now.
Alright, so I fired up ChoconGV here. This is the virtual machine VMware version. Does not need any special hardware or anything. So first we need to put this in English. So to do that, we're going to open up a web browser, which is actually a document editor plugin. Go and get to the support page, find the ChoconGV English kit. We'll download it. Tell it to save it as an archive file. Okay, then we open it and we'll drag the document out. So now we've created the real object containing the English patch, and we'll open it up. It's actually a variety of virtual objects inside. See, I'm double clicking on them. It's very hypertext-like. We'll go into installation. And if you can see right here, the update is actually a blob within the document. So we'll go ahead and go to System Setup, Version tab, drag it in here. Wants us to reboot, we'll go ahead and do that. Alright, then we'll open the document again. Actually, before we do that, we need to switch the language to English. Another reboot. Okay, now we're in English. We'll open this back up again. And what we can do here is if we... Actually, here's an even cooler way of doing this. We can right-click on it here, go to Real Object, Virtual Object Network. You can actually see the structure of all the virtual objects within this document. So if we see this right here, we can do copy to tray, and then copy from tray. I guess the tray is what they call the clipboard. And let's see, let's open up a text pad. It's kind of like a basic document. Alright, so how about let's put our English patch inside this document here. As you can see, it's even been moved out of there. Let's see. Oh, let's open up a drawing. Draw some funny little shapes. You can either, I can save it to a new real object or the original. And we can actually drop it right in here, which I thought was pretty cool. But you can also embed individual objects from within there. So those are also embeddable because, again, it's the same document editor. But here's what I thought was really strange. Let's open that web browser again. Let's take this back out. Now we can save as a TAD file. When we do that, and look at that, there's our object right there. We can just plop it right in here. And then if we go to, let's see here, let's save this first. If we go to the same real object, do the virtual object network, you'll actually find that when we save the web page as a TAD file, it actually preserved every hyperlink, but each hyperlink is actually a virtual object. I thought that was rather interesting and fascinating. I'd never really seen anything like that from a system before. So that's all for the Btron demo. Hope you enjoyed.
Hi, it's the last system we're going to be talking about today, and I actually like Btron, the only other one that's still sold today. Unlike many of its contemporaries, especially in the IBM mainframe world, it combines an easy-to-use interface with then cutting-edge computer science innovations like capability security. If you haven't heard of IBMI, you've probably heard of it under one of its many former names. It's sold to almost exclusively average and non-technical small to medium businesses, basically designed to be treated like an appliance. It runs on IBM's normal PowerPC server lineup. Before that, it used to run various kinds of custom PowerPC and its own even custom architecture boxes. There are no emulators for this, unfortunately, real steel only. The weird thing about I is that it's outlived almost all of its contemporaries, and even the ones that have survived don't tend to have a healthy as ecosystem as I. Despite this, unless you work with your average small to medium businesses, you never ever really know I was a thing. I was designed to be easy to learn. It kind of looks like MVS, COS, or 370 mainframes, but it's notoriously broken and hard to learn. A lot of the I feels like it looks similar to the MVS, but it files away the rough edges because they actually have the luxury of starting from scratch. The biggest change is how all the commands were made consistent. Everything is a mix of verbs and nouns and consistent vocabulary. You can just learn these, and from there you can guess most commands. If you don't know the arguments to a command, or even the values that pass into an argument or whatever you see on screen, you can just press the F4 key. That'll bring up a form prompt, and where you can have all the options presented to you and even explained. It'll usually even generate the actual command to run, so you can use it both as a learning tool as a convenience. If you see something on the screen that you're unsure of, you can just press F1 and it'll show context-sensitive help for anything under the cursor. As for how the F4 prompt works, it's because you're not really invoking the program directly. Instead, there are commands that provide lists of arguments with names, types, and other information, in addition to the actual call to the program itself. Interestingly, the values from this get passed directly to argv. You can handle pointers, including buffers passed to your program, we'll come to that soon, integers, and floats, and the raw. The actual interface is also unlike your typical character terminal. On the right side of the presentation there, you can see Wireshark showing a breakdown of the IP version of the 5250 protocol. It's actually based on sending updates to positions of the screen and fields so that the terminal knows where the editable parts are, while the user submits back only the parts that changed. It sounds a lot like your HTML web form. This means you don't have ANSI-like fine-grained control, but since the machine can make sense of what's given to it, it's easy to navigate by cursor. The first thing you'll notice about the interface is it's quite menu-based by default. For example, we can navigate this way. As you notice, the bottom commands are also all consistent. Things like F3 for exit, F12 for cancel, and F4 for prompt, for example, are also consistent. You can also, if we highlight something on the screen and press F1, we'll get context-sensitive help. We can press F12 to exit out of that. We can also mention the command. Press F1, and it'll also start explaining commands and some of our options. So, we hit F3 to exit here. And if we do an F1 here, you'll also notice that the help system is hypertext. If we press enter here, when the cursor is there, we can navigate, and then we can press F3 to exit. The difference between F3 and F12 is that basically F3 exits out of a screen entirely, while F12 will only exit out of one screen. So you see here, I pressed F3 that one time, but here, I can just do an F12 and get over that way. You also notice that each link had a little triangle indicating that was visited before. Next, we can run work active jobs, and that'll show us a little bit more interesting screen. This tends to be sort of what they call a point-and-shoot interface in the mainframe world, and these work with commands pretty much work similarly. You get some options here. You can get F1 for an explanation. Of each option with the little detail view and so on. As well, you can also put in these options here, and you can first do things like delete or multiple files. In this case, we'll enter 5 to get to the work with screen. And we'll just hit enter here and kind of cancel out of that, but as you can see there, it can do multiple things at a single time. For a little bit more interesting screen, however, you might want to shut down the system, but you don't know all the options for it. So what you can do here is you can press F4, and it'll show you an explanation of everything. And the context-sensitive help here works too. You press F1 and on option, and it'll explain it for you. And as well, you can even F4 again to get more options available. And as you also saw, the vocabulary is also consistent. If we want to work with objects in, say, the Advent 2020, this is TQ's library for his Advent to code stuff, and he's doing in COBOL. And the all there is just kind of a special option, almost kind of like an atom, except behind the scenes it's all handles as strings. Scenes there, we can scroll through, and again we get the same point-and-shoot interface. We can hit delete here. As you can see there, when we enter something that we shouldn't, that is, it's not a marked field, it'll give us an error. What we can do is we can press the reset key in this emulator, Control R, and then we can just space over anything we don't want here. So I'm probably not going to delete his things, but as you can see here, if we press enter, it would delete his stuff there. But even though it would prompt, I'm going to be a nice person and not going to do that. So that's just kind of a quick overview of what the interface is like on these systems. Part of the appliance nature is that SQL is built in the system and even implemented at the kernel level. Despite that, it's basically built on the same primitives of the rest of the system. The same record files that source code is stored in are used for SQL tables. A variety of richer objects that aren't bags of bytes provide the basis for more complex objects. The interesting part is how you store and work with them. There is no traditional file system in the sense that hot data of memory becomes cold data on your disk in a separate structure. Instead, all objects are stored in a single address space. Each object has an address that persists even on reboot. If the data isn't in RAM, it'll be paged in through page faults, and committing it basically flushes changes back to disk, kind of like mmap on Unix. The interesting part of this is you can simply work with pointers from other programs like your own and hold on to them without worrying about them disappearing when the program dies. It changes how you think about buffers or even the difference between programs and processes. Think of the term orthogonal persistence. How is this even secure? I is probably the most popular example of a capability system in the wild. Each pointer is actually 128 bits, 64 bits of metadata and 64 bits of address space. Outside of a pointer is a tag, which when written to invalidates the pointer. Since only trusted code in the kernel can generate the tags, they function effectively as capabilities. The tags are stored in ECC. It uses some unfortunately undocumented PowerPC extensions to actually work. Using machine-independent bytecodes is the other part of the security model. Since native programs aren't allowed, well, except outside of the NAIC syscall emulator, but that's a long story, all programs get compiled to native code by the trusted translator in the kernel. This enforces the security model, like, say, how a JVM would work. It's even allowed the transition from their custom sysc processors to PowerPC, and even allowed them to change the kernel ABI. We're going to show you a demo of some of the behind-the-scenes tools of IBM-I. Unfortunately, a lot of this isn't too well documented because it's usually intended for IBM technicians, but we'll show you here. The next thing we're going to take a look at is SST, the System Service Tools. These provide some low-level insight to what's behind the curtain on IBM-I. It's usually intended for technicians or people who have to get information for technicians. So, we'll start it. It has its own separate credentials from the rest of the system, because this is probably something you don't want to give people that don't need it. From this one, you can do things like work with disks or VMs that you might also have common use for. In this case, we're interested in the service tools. And with service tools, you get things like being able to trace the kernel, as they call it, licensed internal code in IBM speak, the kernel logs, kind of like a kernel syslog, and storage.manager, that's the crashes. But we're interested in particular is display alter dump. This has a bunch of things like special commands, a hex editor that lets you look anywhere in memory, which is really interesting in the system with a single level store. And again, you can also take a look at the structure of objects, which, since this isn't a bag of bytes system, but rather deals with structured objects, is again interesting. So we'll take a look. Display and alter storage. The dump to printer is pretty much the same, except it'll just print out to a spool file or an actual printer if you have one. We'll take a look at an object, and we'll take a look at a program, which it has some special support for. For a lot of these objects, they can display the actual structure, but in addition to the structure of a program, it can also display disassembly appended to it. So we'll do that. We know the name and context name. That's the reason why it's called the context here is because libraries are built on lower level primitives called contexts. And we'll put in one of the programs that TQ wrote for advent to code. These are in COBOL, but it doesn't matter. They all compile to the same bytecode. We'll enter the Advent 2020 library. See there, it found it. That's who wrote it. And if we take a look at disassembled code, it would have the base structure stuff. But in addition, it's also got the disassembly to it. So a lot of this information, you'd pretty much have to work for IBM or at least know a lot about the system to get a lot of it. But things like hex dumps, the actual base kind of structure, that's all pretty interesting. There's things like a string table, but we're also interested here is the actual disassembly. And see there, it looks like a normal PPC disassembly, except there's a bunch of weird instructions like set tag and txair. So, as you can tell here, this probably isn't the PowerPC assembly that you're used to, even if you are used to PowerPC assembly. But that's pretty interesting. Why don't we take a look at what the actual object looks like? So I should have probably F12 there instead of F3'd, but it's nice enough to remember that. And we're going to go into the hex editor. This is capable of making alterations, but we probably don't want to do that. Here we just kind of want to scroll and actually take a look at things. But this assembler has some interesting features like being able to decode PowerPC instructions that are there. If you enter I there, it can also do things like follow pointers and such. But we're kind of done with that. Now let's take a look at a different kind of object. That's a little bit more interesting. We're going to take a look at the system entry point table. This is just basically a big list of pointers that point to basically the entry points of programs. Nothing too crazy, but it also has tags in it, which is going to be pretty interesting to see in the hex editor. So what we're going to do here is we're going to look for the spaceless kind of object. This case is this object type 19 in hex. And it's number 25 in the menu. We'll take a look at the object. We'll put in the name here. And it has a special object subtype of C3. We need to know this because it doesn't really know how to deal with it otherwise. So it's found it. And we'll take a look at base structure. It's nothing too crazy here. Again, this would make more sense if you worked for IBM. So we'll have 12 here, and we'll get into the hex editor. As you can see there, scroll down far enough. The T here is for tag. And those over there are just bunch of pointers. So that's basically SST in a nutshell there. There's more service tools, but this kind of gets you sort of a good idea of what's behind the curtain, what's kind of not really well understood. But it would certainly help if you had to send to IBM. Anyways, that's it for IBMI. We'd like to thank you for coming to the end of our vintage computing bullshit you can learn from session. But wait, we've got more.
That's right. We do have more. In fact, you can try almost everything we've shown you at home. We've got some emulators here for Genera, Enterlisp, and it is possible to get your hands on Chokanji and run it in VMware. That's an exercise up to the reader, but you can probably find it if you look around. But unfortunately for IBMI, there's no emulator. And if anyone wants to rise up to the challenge, go right ahead. We would love to see it. And we also have some additional resources on Enterlisp, Btron, Genera, and IBMI right here. And we also have an IBMI hobbyist Discord. We hate Discord too, but hey, it brought a bunch of enthusiasts out of the woodwork, so we can't complain. It's also bridged to an IRC channel for the traditionalists like us. And that's it, everyone. Thanks for your time. Hope you enjoyed watching our presentation.
It was a quite fascinating talk, and I see why you called it What We Have Lost, because yeah, it's quite a lot that got lost in the progress of the dominance of the PC. And yeah, we got some questions actually, and yeah, I would just dive right into them if there is nothing you would like to add.
TQ?
Oh, yeah, nice. We got the third one.
Yeah. Okay, nice.
So someone in the IRC asked, what does it mean for a computer to be a Lisp machine?
So, it's really, to me, there's two main points. First of all, on a Lisp machine, the instruction set and entire system architecture is built around the idea of running Lisp. And so you had features like garbage collection in microcode that you had hardware management of Lisp arrangement or list arrangement. So, for example, you could not tell from a user perspective whether a list was stored as just contiguous cells of memory or an actual linked list. Integers were all infinite precision. I think that I mentioned that this caused problems for the C compiler because size of char was 1 and max char was infinity. So, the other feature, though, which I think is more important, is that all of the software on the machine is running Lisp. There's no operating system underneath it written in C. There's no assembly component. It's all just, so if you want to replace the drivers or build a driver for some additional hardware that you've attached, you can do that entirely in Lisp. There's a tale from one of the Symbolics field engineers about the fact that at one point they had a customer with a machine that was running very slowly, and they couldn't figure it out. And it turned out that they had installed a patch which replaced a bunch of the drivers on the system, and they never compiled that patch, and so it was interpreting the driver code. And it was slow,
The arithmetic
but
instructions
everything just worked.
operated on
And
arbitrary
yeah, I think that's
precision
really the core of it.
words.
What about Interlisp, though?
I don't actually know that much about Interlisp. You'd have to ask TechFury.
Interlisp, it seems, doesn't really do as much in fancy hardware and microcode as Genera does, and I think a lot of this is because the hardware it ran on, the D machines, was really mainly meant to run Xerox's Mesa virtual machine, and so they kind of just hacked Interlisp onto it by coming up with new microcode, so I think they kind of just had to work within the constraints of that. So for the most part, you don't really see things like hardware garbage collection, or rather microcode-based garbage collection. You do see the basics, though, like the fact, like car and cons and such are all basically literally mapped directly to opcodes. That's probably the biggest thing I've noticed from digging into the D machines.
Yeah, my impression is it's basically West Coast versus East Coast Lisp machine. It's a Biggie and Tupac of computer science.
Well put, Calvin. Well put. All right, I think we have another question. Who still uses the Btron system? And the HTML export functionality seems semi-recent. So, to my understanding, it's basically mostly a legacy platform at this point. It, as far as I understand, has a contingent of academia users, mainly humanities, who tend to use it because it has better support for, shall we say, old/deprecated kanji characters. And I think it's just kind of stuck with some of them through inertia mainly. And I believe the HTML export stuff showed up sometime around the turn of the century, give or take, probably when the changeover to Btron 3/BWrite-V/Chokanji, which would have been about 98, 99, 2000, give or take. So I think it's about when that ended up in there. All right, and it looks like our next question is, what's the most recent advanced or interesting Lisp machine? What do you think, TQ?
So the cheeky answer is Emacs. Because, yes, there is a C core to it, but all of the interface functionality and all of the interaction is purely Lisp. The answer to the question that you were probably asking, though, is that there isn't really an answer. You've got the Genera side and the Interlisp side don't really share any. They don't share a common ancestor. Lisp was very popular in academic and AI communities in the 80s and very early 90s. And so Symbolics commercialized the first Lisp machine, but Xerox came along and developed their own, starting from scratch, and came up with Interlisp. And the two were developed in parallel and didn't really cross-pollinate very much. So Interlisp is still maintained, and it's worth using. And in particular, Interlisp can be used without any question about legality, because it's all open source now.
Yeah, a VLM source is kind of floating around, but the owner of rights is still unclear. Interlisp is explicitly free software now. And one thing to add, I do find it amusing that both Interlisp and Genera share not really common ancestor, but a common sort of source platform of a PDP-10.
Yes, the Lisp classic, the PDP-10.
The PDP-10 is a beautiful machine. I could give an entire talk on its instruction set.
Right.
Sequel bait.
So it looks like our next question, is it really better to run the GC in microcode instead of normal code on an additional core? And that's a really good question, I think. And I honestly wouldn't be surprised if the answer is that no, it's really not. I think that's just what made sense at the time, because you have to remember, at the time they were designing all this stuff, it was just trendy to do everything in microcode. I mean, look at the Xerox Alto. It basically bit bangs all its I/O in microcode tasks.
Much like a Cyrix Media GX came back.
it's not just that it was trendy. At the time, in order to get decent performance running Lisp, you needed to do it in microcode because machines just weren't very fast.
Right.
And we didn't have pipelining, we didn't have the fast memory buses that we do now.
But technically,
It
you may
was-
have, but you had to buy like a 360 Model 90 or a Cray 1 or something like that.
Yeah. And there's no way that you could assign one of those to a single person.
Nope. And the Cray probably wouldn't have been that great of an answer either, because the Cray is really only designed for vector calculations.
Exactly.
So, as it turns out, one of the big reasons that the Lisp machines died is that Franz Lisp ran fantastically on a VAX, and didn't need any of the special hardware support that the Lisp machines offered.
And then basically RISC processors just put the final nail in the coffin.
Yeah, and that's why the registered machines really won, was they just got faster. And even, I think I recall reading that for Xerox Intralisp even, I think by about 87, a Sun 3 Model 60, which is a 20 megahertz Motorola 68020, was already faster than the D machines, according to Xerox's own studies, apparently.
I mean, pretty much every rich environment that didn't die got reported to basically RISC or something sufficiently RISC-like under the hood. I got rebased onto PowerPC. As you know, Interlist actually sort of got a second life running on Sparks. And
Interlist did.
And Genera ran on alphas. But don't worry, we're living the ARM future again. Interlist still runs on ARM.
So I thought this next question was really interesting. What extensions would be required to a normal-ish RISC design to improve Lisp throughput and or latency?
I guess you could add like memory tagging, like one IBM has would actually probably work well for Lisp.
That's a good point.
Memory tagging would be cool.
Yeah, Symbolics did that.
I think the memory tagging extensions for ARM the ARM are only really good for security because they're basically more pointer signing, I think. The Spark ones I don't know much about, but I think they're intended for JVMs, so yeah, Lisp would work.
The Spark instruction set, or the Spark extensions, as I understand, were actually specifically designed for Lisp. They give you 2 additional tag bits for types.
Really?
And arithmetic instructions.
I thought they were more designed for the JVM. Sun.
I believe that the arithmetic instructions trap if the tag bits aren't the same for 2 pointers, and so you can just you can pretend that everything's a fixed num and handle it if it's not.
Yeah,
that makes sense.
That sounds like it would work for a JVM, but what works for a JVM would probably work for a Lisp. Yeah, and what's little known about the IBM extensions, all they really do is there's no hardware enforcement. Rather, it's just like acceleration for basically software-based checks.
So actually, one feature that's surprisingly good, is surprising at accelerating Lisp code, is floating or IEEE floating point. Look into Nanboxing if you haven't, because it is.
I've heard about Nanboxing, yeah.
Yeah, it turns out that you could store pointers and most types in the unused bits in not a number. And they'll trap if you try to add 2 things that aren't numbers.
Oh my god, NAND singling.
Yeah.
Dangerous.
Oh god, that's cursed, but I like it.
Right.
It really is.
Yeah, so I'm afraid we'll have to cut it a bit here because we're running a bit short in time.
No worries.
So there are 2 questions left, and one personal remark. The first one is if the beach one situation is similar to what happened to OS2's respectively ecom station.
So I'm not sure if you can really draw an analogy there, because Ecom Station is kind of a, if I recall correctly, the whole arrangement with Ecom Station is that it's a OEM distribution of OS2. but it's a little bit different with Btron because Btron is an open specification that realistically only one vendor really made implementations of personal media.
Imagine if basically there's only a single POSIX implementation standing. That's basically it.
What he said.
So, and I think someone asked, when are you going to give a talk on the PDP-10?
Maybe next year?
Oh, yeah.
Hopefully.
That's. I think that was then quite easy to answer. And someone personally remarked that they have a 60-page paper on the Tron in case someone was listening on the IRC. But it's in German, so yeah. If you speak German, maybe this person can. Maybe this person will be will suit your needs. Also, there was the request from the IRC to the speakers to maybe hang around a bit longer in the IRC to answer any additional questions there, because we sadly have to end the talk as your time slot. So yeah, thank you for taking the time to prepare all this. Thank you for joining us from such remote locations. Thank you for standing up early or late.
Well, it's really early for us, so.
Yeah, so thank you very much for that, and have a nice remote chaos experience. Thank you.
Thank you.
Thank you for your talk.